Hello everyone. Today we will be going over parametric equations, and throughout this video there's a good example that will help explain the idea of what a parametric equation is, and throughout the video it'll make more sense rather than me trying to explain it right now. So basically what we have right here is, we'll pretend this is like a platform, and we have a dirt biker up at the top that's going to be jumping down this way. And through a parametric equation, we can figure out at what rate he's going, his slope going downward is. And through parametric equations also, we can figure out that it is a downward slope. So, first off, here's going to be our dirt biker. And trust me, the graph will look better than my attempt at a dirt bike. So there's our dirt biker up there. He's all excited. He's going to go down. He's going to jump this ledge. And let's just say this ledge is up here. This whole box, it's 5 meters long this way. And he's 30 meters high. So if we think of this like an XY graph, here would be our y-axis. Here would be our x-axis. So I'm going to draw that just for us right now. There's going to be our y. Across the bottom right here is going to be our x-axis. X and a y. So this will be our time at 0, essentially. We can say that time is 0 because his jump and acceleration will start once he passes that point. And we'll say his speed of travel is right about 8 meters per second. So he's going to be going this way at 8 meters per second. So first off, we need to figure out x as a function of time. So how fast he will be going to the right. How fast he'll be going to the right. And then later we'll figure out y as a function of time, which is how fast he's going to go towards the ground. So first, for x as a function of time, I'll do it up here. So we have space to graph below. X as a function of time, and t is our time, will be 8, because he's going 8 meters per second. So it will be 8t, and he's starting 5 meters in. So just like a normal graph would be, it would be plus 5 right there, because we're not starting at 0 over here, we're starting 5 meters in, although that is our time at 0. So then next we can figure out our y as a function of time. So same, y as a function of time will equal, he will start at 30 feet off the ground. So we'll do 30 there, and we know he's going to be going down, so minus. And although this is pre-calc and this is not necessarily physics, some physics does come into play in this, how fast he will hit the ground. So gravity, this is just a known physics fact that I won't get too much in depth into, but gravity is pulling an object down, all right, gravity there, so we know, is pulling an object down at approximately 9.8 meters per second squared. So to make things a little easier, we can say that is about 10 meters per second squared. So right up here we'll write minus 10 times squared all over 2. And don't worry too much about knowing that equation, because that's physics, and if this was a pre-calc test or something, that would be given to you. I'm just that just needed to be known for the example of our dirt biker going down off a cliff. So after that, basically all we have to do is just figure out and plot our points then, going down to figure out how you go down. So I will make a little chart over here, so it should be out of the way. I'll do it right there. Our time, X and Y, and just a little simple T chart. And so I'll say we'll do 0, 1, 2, 3. And those are just numbers I'm picking as time goes on. As time goes on in seconds, because that's our time at 0 seconds. So as time goes on this way, essentially, that's how I got the 1, 2, 3. And if you wanted to pick 0.5, 1, that's totally up to you. That's just whichever numbers you want to pick progressing forward so that you can get an accurate graph. So essentially all we have to do from now on is just plug 0 in to this equation, and if you plug 0 in for that, 0 times 8 is 0 plus 5, so our x value is going to be 5. And if we go right there, that makes sense. He's 5 meters in. I might as well write that at the bottom to make things easier. Might as well right now mark the sides of this. Actually, let's go by. Go by 5, 10, 15, 20, 25, and there's our 30. Going across this way then, we can go by 5s as well, so 5, 10, 15, 20, and then we'll see how high we have to go based on our T-chart up here. So then 30, first off, actually, let me back up for a second. We can reduce this so we're making our life a little easier. Instead of 10 times t squared over 2, we can just make that 5. But I'm going to rewrite it right here just so it makes sense. Slash 30 minus 5t squared. So that when we plug stuff in, we can make it a little simpler for ourselves, because that's just reducing. So when we plug that in right there, 0 squared is 0 times 5 makes that 0, so it's 30. And that matches up that we're 30 feet off the ground. And we're starting 5 meters in. So far, our math is correct, and that makes sense how it's 0. So now as we go on, we will just simply plug it in. So 8 times 1 is 8, plus 5 will give us 13. And I'm going to do all of the x's first and then all of the y's, just so I'm not flipping in between equations. If you want to do each equation, if you want to do ones all for the same, that's up to you, but just make it easier so I don't make a mistake. 8 times 2 is 16, plus 5 is 21. And then 8 times 3 is 24, plus 5 gives us 29. So then for y then, I'll plug it into that. So 1 squared is 1 times 5 gives us 5. So 30 minus 5, which is 25. 2 squared is 4. So 5 times 4 is 20. 30 minus 20 gives us 10. And then I can already tell that this number is going to be in the negatives. So we can tell by the time he gets to 3 seconds in, he's already going to be below. But let's just do it anyway. So 3 squared is 9, times 5 is 45, minus 30 minus 45 gives us a negative 15. So yeah, we'll be in the negatives down here. But I see our highest number there is 29. Even though it's negative, I'm still just going to continue this up to 29. So 20, 25, and 30. There, we fit it all in. So then from here on, it's not too bad. It's just plugging in the points. So here's essentially our point would be 5:30. And our point is 13:25, 21:10, and 29:15. So it's not too bad from here on. So 5:30 gives us that point, which is our time at 0. Gives us that 0. So our time at 1 second would go about 13. And this will eyeball just so we can get a basic shape. So 13, we're going to go all the way up to 25. So that is right about there, let's say. And then for our next point, we'll go to right about 21. And then we'll go up to 10, which is only right about there. And then for our last point, which is going to be negative, but I still want to know where it will go, just so I can get a better shape of this, will be 29, and then probably -15. I eyeball it at right there. So if we start to connect dots up here, we see that is about where it came down at. So it came down somewhere about 25, 26. Which is nice because about this, we always know where the dirt bike is because we have the graph right here, and if we want to plug any of these numbers in below, any of these x values or any of the y values into this equation or that equation, we can essentially figure out where the bike is at any time. So that's why, even though I don't know exactly where it went down, we can assume that it's somewhere 25, 26, maybe even 24, but it's right about right there. So basically, we define x and y as a third-party parameter of t. So a parameter is just a way of measuring something. So most of the time when you're given an x or a y value, you have those two variables. But with a parametric equation, with a parametric equation, you can solve for this third parametric, which in this case was our time, so we can figure out across how many seconds it took for our dirt biker to perform its stunt and go off this ledge or this cliff up here, with a little bit of physics of gravity pulling him down 10 meters a second. And then another good thing about parametric equations is we know the direction of travel. A lot of times if you were just given this graph, which is somewhat of a half semicircle, you don't essentially know which way the direction of the graph is going. It's easier with parametric equations. We know as we graphed it, our points got lower and lower, so we know gravity is pulling him down, although in this case, obviously we knew it was gravity was yanking him down, but we knew that the points were getting progressively lower. And with a parametric equation, it's very easy to figure that out. So we'll throw some arrows on there, just so we know that, hey, this parametric equation is going downward. As time increases, we go downward, which makes sense. And yeah, that is how you graph a parametric equation. Thank you.